Hello everyone, welcome to MLRIT. I'm Noel Nalli, working as an assistant professor in physics, Department of Science and Humanities, MLR Institute of Technology, Hyderabad. In this lecture, let us discuss about Hall effect. Before discussing about Hall effect concept, let us summarize previous lecture. In previous lecture, we discussed about formation of PN junction diode, working of PN junction diode, that is forward and reverse bias, VA characteristics of PN junction diode. Of course, these all things about semiconductors. Apart from these topics, in this lecture, we are going to discuss about Hall effect. Anyhow, Hall effect is a general concept, but which is a very important concept in case of semiconductors. So that in today's lecture, we will discuss what is Hall effect and Hall coefficient expression and applications of Hall effect. Without delay, let us see what is Hall effect phenomena. I hope many of you know about Fleming's left hand rule. Here you can see this is the Fleming's left hand rule concept. The thing is, when we apply a magnetic field to a current carrying conductor, that is both magnetic field and current both are perpendicular. That is, when we apply a magnetic field or when we apply a magnetic field to the current carrying conductor, then there exists some force perpendicular to both magnetic field and current directions. That is, from this image, you can observe clearly. In this image, you can observe that here along x direction there exists current flow. Along x direction there exists current flow, and we applied magnetic field along z direction. Due to these current and magnetic field, there exists some force on the charged particle perpendicular to both current and magnetic field direction. That is along y direction. That force is nothing but Lorentz force. Due to Lorentz force, if that specimen or if that material is a semiconductor material, whether it is semiconductor or conductor, if that material is a semiconductor material, electrons are going to accumulate on opposite phase due to that Lorentz force. And similarly, if electrons are going to be experience a Lorentz force along y direction, similarly negative y direction holes are going to accumulate on opposite phase. So that in between these two phases, some potential is going to be developed. That developed potential is called Hall potential, and this effect is called Hall effect. Let us see what is Hall effect phenomena. When a current carrying conductor is placed in a magnetic field or transverse magnetic field, when a current carrying conductor is placed in a transverse magnetic field, that is both current and magnetic field, both current and magnetic fields are perpendicular to each other. In such a way, when a current carrying conductor is placed in a transverse magnetic field, then there exists or then the potential is going to be developed perpendicular to both electric and magnetic field direction on opposite phases to that specimen. This developed potential is called Hall potential, and this developed potential is called Hall potential, and this phenomenon is known as Hall effect. Now, let us see what is Hall effect, Hall coefficient, because this Hall effect concept is variously used in different sensors to measure magnetic field, to measure current, and to measure voltage. In different sensors, this Hall effect concept is going to be used. Now, let us see what is Hall coefficient. Now, anyhow, here you can see a simple illustration in this image. Here, current is passing in this direction, you can observe, and magnetic field is applied. For example, magnetic field is applied in x direction and current is passing in z direction. And here you can see, due to Lorentz force, electrons are going to be moved perpendicular to both current and magnetic field direction. So that perpendicular in this specimen, both perpendicular to current and magnetic field, some potential is going to be developed. When it is short circuited, perpendicular direction, there exists some potential or there exists some current flow due to Hall effect. I hope it's clear. Now, let us see what is Hall coefficient. Now, anyhow, here you can see, due to that means according to Fleming's left hand rule, here middle finger indicates current direction and index finger indicates magnetic field direction. So, according to Fleming's left hand rule, there exists some force perpendicular to both current and magnetic field direction. That means along thumb direction, some force is acting on the charge carriers. That force is nothing but Lorentz force. here I'm going to take Lorentz force expression. When a perpendicular magnetic field is present, Lorentz force is exerted on the electrons due to electrons move perpendicular direction to both current and magnetic field direction. That Lorentz force expression is FL equal to QVD cross B. Directly here I am taking Lorentz force expression, FL equal to QVD cross B. Q is nothing but charge of the charged particle. Vd is nothing but drift velocity. Normally, in a conductor material, there exists random motion of electrons without applying electric field. But whenever we apply electric field, electrons are going to electrons are going to drift according to that applied field. That drift, that means due to electric field, there exists some drift velocity in that electrons. That velocity is nothing but Vd, drift velocity, and B is nothing but magnetic field intensity. So that whatever that Lorentz force is acting on the charged particle, that is QVD cross B. Here, drift velocity and magnetic field are both vector quantities. So here I am going to take QVD cross B sin theta. Anyhow, in between electric field and magnetic field, angle theta equal to 90 degrees. So that here, instead of theta, when we take 90, directly we can write Lorentz force is equal to FL equal to QVDB. This is Lorentz force due to electric field and magnetic field. Now, due to these Hall effect or due to these Lorentz force, some potential is going to develop on opposite faces. Here you can see some potential is going to develop on opposite faces. Due to this potential, in between these two faces, some electric field is going to be developed, EH. Some electric field is going to develop. Due to that electric field also, some force is acting on the charged particle. Of course, I hope you all know that electric field equal to E equal to F by Q, force per unit charge. So, from that expression, we can write force on the charged particle due to electric field equal to, we can write F equal to QE. But here, that force is due to Hall electric field. That's why simply the force due to Hall electric field, we can write FH equal to QEH. Now, if that material is at equilibrium, then these two forces are equal. So that now, if that system is at equilibrium, we can equate 1 equal to 2, that is FL equal to FH. If FL equal to FH, we can cancel both Q's. Then simply we can write EH equal to VDB. I hope you know that VD is nothing but drift velocity, B is magnetic field intensity, EH is nothing but Hall electric field. Now, we know that drift velocity expression in terms of current density. Directly I am taking this expression. Vd equal to J by NQ. J is nothing but current density, current passing through unit cross section area. N is nothing but charge carriers per carrier concentration, charge carriers per unit volume. Q is the charge of the charged particle. So now we are going to substitute this drift velocity expression in this expression EH equal to VDB. Now when we substitute, we can write EH equal to JB by NQ. Here 1 by NQ is known as Hall coefficient. RH, which is going to be represented with RH. Here 1 by NQ, RH equal to 1 by NQ, that is known as Hall coefficient. So we can write EH equal to RHJB. From this, we can write RH equal to EH by JB. Hall coefficient in terms of Hall electric field, current density, magnetic field intensity. I hope it's clear. Now, the Hall coefficient expression is RH equal to 1 by NQ. I already told you, N is nothing but carrier concentration, number of charge carriers per unit volume. Q is nothing but charge of the charged particle. Now, by knowing these values, we can calculate Hall coefficient of that material. Now, again, Hall coefficient expression in terms of Hall voltage. Hall coefficient expression in terms of Hall voltage is RH equal to VHT by IB. VH is nothing but Hall potential. T is nothing but thickness of that material. T is the thickness of that material. And again, current is I is nothing but current. B is nothing but magnetic field intensity. So, by using this Hall coefficient, the very important concept is by using this Hall coefficient, whether the given semiconductor is N type or P type, that can be identified by measuring the Hall coefficient of a semiconductor material. Not only that, number of applications are there. By using Hall coefficient, we can measure the Hall voltage, or we can measure Hall electric field, or we can measure carrier concentration. Such number of applications are there. Apart from that, very important applications are these Hall effect concept is going to be used in sensors. So now let us see applications of Hall effect. Now, when it comes to the applications of Hall effect concept is used magnetic field sensing equipments. Magnetic field sensing equipments, that means by using that equipments we can measure the magnetic field intensity. Apart from that, this Hall effect concept is going to be used Hall effect tongue testers. Here whatever the device here you can see, that is nothing but Hall tester. By using this tester we can measure AC current, DC current, we can measure voltage. Number of applications are there by using this tester. And not only that, it is used in phase angular measurement devices and Hall effect sensors and probes. These all are for measuring magnetic field, current and such applications, and linear displacement transducers. That means we can measure linear displacement or angular displacement of an object by using that linear displacement transducers or angular displacement transducers. Not only that, for detecting wheel speed and accordingly assist the anti-clock braking system. These Hall effect devices are going to be used. Not only these applications, many applications are there to these Hall effect concept. In that few applications I mentioned. This is about Hall effect. Let us summarize today's lecture. In this lecture, we discussed about what is Hall effect. Simply, Hall effect is nothing but when we apply, that means when we place a current carrying conductor in a transverse magnetic field. Here you can see when we place a current carrying conductor, current carrying semiconductor, whatever it may be, in a transverse magnetic field, that is both current and magnetic field should be perpendicular direction. Then the potential difference will be developed in opposite phases perpendicular to both current and magnetic field. That is known as Hall effect. After Hall effect, we discussed about Hall coefficient expression, RH equal to 1 by NQ. By using Hall coefficient, we can study many properties of conductors or semiconductor materials. And after that, we discussed about applications of Hall effect. Thank you.